Alright, on to part D of this problem. So, this problem especially is really easy if you have the proper background, but really difficult if you don't have the background. Really, what this is dealing with metric space topology, which you cover pretty early on if in like a point set topology course, like your first course in topology. But if you haven't had that, then it's a little tricky, and there hasn't been that much point set topology yet in this textbook, so it can be really tricky just to take what you've been shown so far and to try to do something with it. But anyways, let's go from here. So, see here, since A is open, and well, actually, before I get into this, let me actually explain what we're going to do. So we have a compact set C, and then outside of it, we're going to have a closed set B, and this is all going to be contained in some open set A. So let's see here. So A is open, B is closed, and C is compact. And what we're going to do is we're going to find a function which is strictly positive on C and strictly zero outside of B. So basically what we're going to do is we're going to take a whole bunch of squares in here. So this is a subset. This is all in taking place in Rn. And so we can cover Rn using squares. And so what we're going to do is we're going to cover this whole thing with squares. And then we're going to define, take functions g from part C of this problem, and define a function on each of these squares, and then sort of add all of these functions together, and we'll get a function which is strictly positive on the union of these squares. And another thing to note here is that we want to choose these squares in such a way that we want to be able to cover all of C, and we want the squares to be in A, and we don't want to go outside of A. So like if we choose like a really large square like this, then sure, this square covers part of C, but it also goes outside of A, and we don't want that to happen. So let me erase some of these. And so let's start with the exercise and see what we're going to do here. So let's see here. Since A is open and C is compact, it's a compact subset of A. D, which we will set as the distance between the boundary of A and C. And what is this? This is something that you might not have seen if you haven't talked about metric spaces before. So it might not be natural for this to occur to you, but that's okay. So the distance between delta A and C, basically what you mean is you take all possible lines that go from the boundary of A to C, and you take the length of that line, and you try to find the smallest length possible. So what this is actually defined as, it's the infimum of all things of the form A minus C, where A is an element, where A is a point on the boundary of A, and C is a point inside of the set C. And since A is open and C is compact, if D is defined to be this thing, then D is strictly greater than 0. i.e. there is some there is some distance between C and A. Like sometimes you could imagine, like, if you had just two arbitrary sets like A and B here, you could imagine it's possible that this subset on the inside like gets really, really, really close to the boundary of the larger set, in such a way that this infimum here, if you define it for these two sets, the infimum would be 0. However, what I'm saying is that this is not the case. That this minimal distance between the two sets, between the two sets, boundary of A and all of C, the minimum distance is strictly positive. And if you've taken a metrics, if you've learned some metrics-based topology before, then this might be something that you know already, and maybe you can just go from here. If you don't know this fact already, I'll just go into a little more detail. I don't know how much detail I would need to go in order to provide the background necessary for this course. I didn't take a super close look at all of the different facts and theorems and exercises that have been presented so far on point set topology. I'll go into enough detail that any additional detail you should be able to figure out on your own, or worst case scenario, you just pick up a copy of Munkers or Munkries, however it's pronounced, and learn a little bit about topology. The chapter 2 of Baby Rudin would also work. Yeah. Okay, so D is strictly greater than 0. Now, to prove this, assume for contradiction that D equals 0. A lot of these exercises in basic point set topology are really easy if you use contradiction, and it's sort of the easiest way to do them. Again, contradiction proofs are not always the best, but here it's fine. So assume for contradiction that D equals 0. Then D, now it's the infimum of the distance between delta A and C. Well, it's the infimum of all points of this form. And we could also write it as the infimum of the distance between the boundary of A and the point C for every C in capital C. And this is something that you can take the time to actually prove yourself. Because, well, the infimum here, this is defined to be the distance between delta A and C is just the infimum of A minus C, where A is on the boundary of A. And so if you combine these two things together, you see that what you end up with is the same number lowercase d that we had before. Okay, so anyway, so D is equal to this thing. So D is the infimum of numbers of this form. And for D to be the infimum of this means that there is a sequence Cn contained in the compact set C such that the limit as n goes to infinity of the distance between wait a minute. Yeah, the distance between Cn and delta A is equal to 0. No, it's equal to this number D. So when this is just the way, this is just sort of built into the way that infimums are defined. If D is the infimum of all things of this form, then it doesn't necessarily mean that there is some element C in the compact set C which attains this infimum, but it does mean that there is a sequence that will allow you to get arbitrarily close to this infimum. Okay, so we have the distance between this Cn and delta A equals D. Since C is a compact subset of a metric space, Cn has a convergent subsequence. And we'll call it CNM. I guess I should not be using n here, because we're using n to refer to the dimension of the space we're working in. So we should call these CM. So this is CM here, and it has a convergent subsequence CMK. Now this I haven't even defined what a metric space is. So you can either look it up and learn what it is. It's a topological space which has a distance function on it that satisfies all the properties that you would expect something to be called a distance to satisfy. And it's a fact in basic topology that of course, something that you prove that, there's different definitions of compactness. There's compactness in the sense of every open cover has a finite subcover. That's the standard definition, and that's the definition used in this textbook. There's also a definition called sequential compactness, which means that every infinite sequence contained in a sequentially compact set has a convergent subsequence. And these two definitions are not necessarily the same thing. You can have sort of strange topological spaces in which one holds and not the other. I forget which one is stronger or what the relation is between them. I haven't brushed up on my topology, my point set topology in a bit. But in a metric space, compact sets are sequentially compact sets, and vice versa. Sequentially compact sets are compact. So the fact that we have a infinite sequence in a compact metric in a compact set means that there is a convergent subsequence. So the limit as k goes to infinity of CMK is going to be equal to C for some C in this compact set C, i.e. this subsequence converges to an element in C, and I'm just going to call it lowercase c. Since C is compact, it is closed. I believe that's been discussed here in this textbook, that in Rn, a set being compact is equivalent to it being closed and bounded. And so compact in particular implies closed, and closed sets contain their limit points. Oh, okay. Yeah, so this limit is C for some C in, this C is just some element of Rn. We don't know where it is yet necessarily. However, since C is compact, it is closed, so C contains its limit points, and thus C is actually an element of the compact set C. Alright? So now what? So then C is in C, and D is equal to, well, let's see. We're assuming for contradiction that d equals 0. So 0 is equal to d, which is the limit as n goes to infinity of the distance between Cm and delta A, which means that, well, this is the same as the limit as k goes to infinity of the distance between Cmk and delta A, because if the limit exists for the entire sequence, then certainly it exists for the subsequence. But since the subsequence converges to C, this is equal to the limit as k goes to infinity. Well, it equals to the distance between C and delta A. All right. So the infimum of C minus A, where A is in delta A, this infimum is 0. So I guess this by itself does not necessarily imply. Here, yeah. Let me just do the rest of this. So this is sort of I'm sort of doing this. I'm sort of realizing that I could have done this a little more cleanly, perhaps. So anyways, then there exists a sequence AN in A What am I trying to prove? I'm trying to prove my contradiction is going to be from the fact that we're saying here that C is actually in delta A. And let's see here. Oh, right. Okay. Then there exists in AN a subsequence in delta A such that the limit as n goes to infinity of C minus AN equals 0. So AN, the sequence, this is equivalent to saying that the sequence AN converges to C. Since the boundary of A is closed, and that's just by the definition of closed sets, or yeah, by the definition of boundaries, the boundary of a set is always a closed set, because what you do is to get the boundary, you take the closure and you remove the interior. The closure is a closed set, and the interior is open. Removing an open set from a closed set gives you a closed set. Because what you're really, you can think of removing an open set as the same as intersecting the complement of the open set, and the complement of an open set is closed. So you're really taking the intersection of two closed sets, which is going to be closed. So therefore, the boundary of A is closed, and since it is closed, C is in A. C is in the boundary of A. This is impossible since C contained in A, C is compact, and A is open, right? Because right, because okay, that's not the right way to say this. Since delta A is closed, C is in delta A. But what's important about delta A? Since A is open, delta A, the intersection of delta A with A is empty. Because if you take the closure of, if you take the boundary of an open set, none of the points in the boundary are actually in the open set. Because otherwise it wouldn't be open. So since A is open, A does not intersect with its boundary. So, then, what's the issue here? This contradicts the fact that C is contained in A. Because if C were contained in A, then every element of C would be contained in the set A, but we found an element of C which is contained in the boundary of A, and the boundary of A, any point in the boundary of A is not contained in A. So this is a contradiction. Thus, D is strictly greater than 0. Alright, so that's the first part of this. And now, are we done? No, we have quite a bit more to prove actually here, which is not great, but whatever. Now choose delta a positive number delta less than D, small enough that any open n cell I whose edge lengths are all small enough so that for any open n cell I whose edge lengths are at most delta, the closure of this open n cell cannot intersect both C and delta A. Okay, so what am I trying to do here? What I'm trying to do is that if we have like, if we have A here and we have C here, let's do it like this. Here. Okay, so A, C. We want to make sure that our boxes are small enough that if you cover C with boxes, then they won't touch the boundary of A at all. So, for example, if we had a box like this, this wouldn't work. And you see, like, say, like, this distance here is D. This is the smallest distance. We see that, like, in this particular example, if we choose, if we make our boxes really, really small, then there's no, like, if we make the boxes have side lengths a lot smaller than D, then there's no way for a box to intersect both C and delta A, just because there's too much distance. It can't cover the entire distance D. Now, why did I go through all this trouble and not just saying choose any delta less than D? Now, if we were going to cover the set A with open circles, open balls in Rn, then I think you could just choose delta to be any number strictly less than D, possibly even equal to D, but I don't want to worry about that. The thing about boxes, though, is that they have corners, and so you have to worry about that. Maybe if you, because like the longest distance from like a point in this, from the longest distance between 2 points in a box is if you go between the two corners, in which case you just take like, you throw a square root of 2 in there or something. Like you if you want to choose, if you want to actually choose the mathematical best the largest possible delta to make this work, you would have to throw a square root of 2 in there relative to d, so maybe it'd be like, yeah, I don't know what it would be. It doesn't really matter. All that matters is that you can choose some delta small enough. Like maybe delta is like d divided by 3 or 4 or something like that. I don't know for sure, but there's something that you can get which will guarantee that any open n cell I will satisfy this thing that I've just said here. Okay? So anyways, so we're going to keep this delta in mind. And also, for any n cell I, of course an n cell here is just the direct product of n intervals. So anyway, so for any n cell I, let the r of I denote the radius of I. So denote the length of the longest edge of I. And we're going to define script I to be the set of all n cells contained in the set A such that I, of course, is an n cell and the radius of I is less than or equal to delta. So basically we're going to take very small squares inside A and just like consider all sufficiently small n cells that can fit inside the set A. Okay? Now, since A is open, A can be written as the union of all n cells contained in A. Well, certainly A can be written as the union of all n cells contained in A, but furthermore, you can restrict all of these n cells to be as small as you want. So you can put an upper bound on how many n cells you want to consider. And this is fine. So anyway, so this is this set I here. This is uncountable. It's a very new. There's a lot of things in this set. There are a lot of n cells that you could put in here, but we don't care about the size because we know that A is the union of these things, and we don't care about how many elements are in the set because we're going to get rid of them right now. So since C subset of A is compact, or since C is a subset of A, script I is an open cover of C. So now you should sort of be able to see what we're going for. We're trying to use compactness here. Since C is a subset of A, script I is an open cover of C. So by compactness, there is a finite subcover. And we'll just call this capital I1 through capital IM. Okay. For each I cell, capital I, lowercase I, we know by part C that there is a C infinity function GI which is supported on this I cell. So again, when I say it's supported on the I cell, I mean that GI if you evaluate GI at any point inside this I cell, then you'll get a positive number, strictly positive. And if you evaluate GI at any point outside of II, then G will evaluate to 0. Okay. Now we're looking for a function f here. Again, this is really bad notation again, because now we have another function f. So in the way that Spivak's written this textbook, this is the third function f. This is the third time we're using the letter f to refer to a new function in this one exercise. This is not... anyways, so I am going to go ahead and call this f, because from here on out we're not using any of the previous f's, so it's not as big of an issue here. But anyway, so let f be... Well, let me just for notational purposes, write it f of x. F of x is going to be written as the sum from I equals 1 to m of gi of x. Then f is always greater than or equal to 0, because if you evaluate at any point x, each gi is going to be greater than or equal to 0. So if you add up a bunch of them, you're also going to end up with something that's greater than or equal to 0. What else do we have? F is a C infinity function because we're taking a finite sum of C infinity functions, and when you take the derivative of a sum of different functions, you just take the derivatives of each of the functions individually and add them up. So finite sums of C infinity functions are C infinity. So that's that. And f is supported on the union of I equals 1 to m of I. If we let B be the union of the closures of these n cells, then C is contained in B is contained in A. C is contained in B because B is just the closures of an open cover of C. So in particular, B is a cover of C. And more importantly, B is contained in A because of how small delta is. That's why we had to go through the trouble of defining delta, is to ensure that we can get this closed set B, which is contained within A. We had to be sure that we wouldn't end up with a scenario where we have this open cover of C, and then we take the closure of this open cover, and we end up with points on the boundary of A. We had to make sure that that couldn't happen, and we did that by choosing delta sufficiently small enough. So then this is true, and f is equal to 0 outside of B. And this is because f is equal to 0 outside of the union of the n cells, and the union of the n cells are contained in B, and therefore f is 0 outside of B. Alright. This completes part D. Alright, now there was another thing that I was going to do here, because for part E, there's something else that you have to do with this function f. You need to ensure that this function f is greater than or equal to epsilon on the compact set C. And so I take a little bit of extra time to do that, and I was going to do that here, but considering how long this video is, I don't want to this video is really long already, and the next video isn't going to be super long, so I'll just take that part and throw it on the end there. And so, yeah, this finishes this part of the problem. I'm sorry if there was a lot of stuff in here that you didn't understand. If you need to, you can always look up Moncrief or Baby Rudin to get some background on point set topology to help you out. But yeah, this finishes this part, and now we will move on and start to really wrap up this problem with the next and final part.